So the last part of our section on Introduction to Probability is the discussion of a probability distribution. And what a probability distribution is it gives you the entire range of values that can occur based on an experiment. And so there are three main characteristics of this. The probability of a particular outcome needs to be between 0 and 1, and it can include 0 and 1. The outcomes are mutually exclusive, or also sometimes called disjoint. The list of outcomes needs to include all possible lists of outcomes. So what that means is when I add up all the probabilities of all the different outcomes, it should equal to 1. And so an example of this would be a manufacturer may claim that a treatment will cause weight loss for 80% of the population. And so what this means is we can take a sample and test to see if we do see weight loss in 80% of the individuals using this particular drug. A probability distribution for a random variable is going to describe how the probabilities are going to be distributed over all of the values of that random variable. And so you can have this depicted in terms of a distribution function, a table, or a graph. So the first of two types that we have is that we can use the rules of assigning probabilities to experimental outcomes to determine the probabilities for each value of the random variable. And then the second type is using that mathematical formula to compute those probabilities for each of the different values of our random variable. And so you can define a probability function by using basically a formula. And so the required conditions for a discrete probability function are that the f of x value, or the probability of x, is greater than or equal to 0, and the sum of all of your probability values needs to equal 1. And so when we're looking at discrete probability distributions, there are three methods of assigning probabilities to our random variables. And they're the three methods that we talked about in our very first discussion about probability. So our classical method, our subjective or Bayesian method, and then our frequency or empirical method. And so the use of the relative frequency method to develop discrete probability distributions leads to what we call an empirical discrete distribution. And so here we have an example of JSL appliances looking at how many days we have a particular number of units sold. So you can look at this in a tabular representation as shown on the left. So here we have a table that says out of 80 days out of the 200 days that we're looking at, we had 0 units sold. And so you can get the probability that the X will occur by taking your number of days divided by your total number of days. So our f of x for 0 units sold is going to be 80 divided by 200 to get 0.4. We can also have this demonstrated using a bar graph, as you see here on the right. So in addition to tables and graphs, we can have a probability function or a formula that we talked about using the f of x format. And so what this is saying is for every value of x, we have a formula that can compute what those x values can be within that range of the probability distribution. And so we have several discrete probability distributions that are specified by formulas, including discrete, which are uniform, binomial, Poisson, and hypergeometric distributions. We will talk about a little bit about uniform and hypergeometric, but mainly focus on binomial and Poisson in our next unit when we are starting to talk about distributions more in depth. So talking about discrete probability distributions a little bit more, that's going to be the simplest example that we have of a probability distribution given by a formula. And so it's usually the one that you're used to seeing, which is 1 out of however many objects you have in your sample, or how many outcomes your random variable can assume. And so here we have an example where we are interested in the number of heads showing face up with 3 coin tosses. So our possible outcomes are all 3 of the outcomes are tails. 1 of them is heads, 2 of them are heads, or all 3 of them are heads. So using the counting formula that we talked about earlier, we know that there are 8 possible outcomes when we're tossing a coin 3 times. that you can observe, right? So you can use the multiplication rule to come up with this to get 2 times 2 times 2 to have a total of 8 potential outcomes, or you can actually draw out all the different potential outcomes as we have here. And so here's a probability distribution table of the charts of the events of 0, 1, 2, and 3 heads, okay? And tossing the coin 3 times once again gives us 8 different outcomes. The event of having 0 heads, 1, 2, or 3 are mutually exclusive and collectively exhaustive. So that means that the sum of the probabilities of all of these outcomes will equal 1. The mean of a probability distribution is the long run average of the random variable. So P of x is going to represent the probability of a particular value of x. So to calculate the mean, you're going to multiply each value of x by its probability of occurrence and then add these products together. The expected value is also called the mean of that distribution, is going to be the measure of its central location. And the expected value is a weighted average of the values the random variable may assume. The weights are going to be those probabilities. Expected value does not have to be a value that the random variable can assume. Your variance is going to summarize the variability of the values of the random variable. The variance is a weighted average of the squared deviations of a random variable from its mean, and the weights are going to be the probabilities. And then also not shown here is the standard deviation, but that's going to be defined as the positive square root of the variance. So here we have a random variable mean distribution example. Here we find John can expect to sell 2.1 cars on a typical Saturday. So once again, our expected value or our mean is not a value that would have actually have shown up in our distribution, because you can't sell a fraction of a car, but that is the central tendency of his distribution. And so what this means is, over the long run, let's say 50 Saturdays in a year, he can expect to sell 50 times 2.1, so he can expect to sell 105 cars. And so let's look at the next slide to see how we would calculate that variance. So to get that variance, we take the number of cars sold and their probability. We're going to do the observed value minus the expected or the mean. We're going to take that value and then square it, multiply that value times the probability, and add all those values up. That value is going to give me the variance. And so then, once we take the square root of that variance, we can now have the standard deviation. So for this example, the mean was 2.1, the variance was 1.290, and the standard deviation is 1.136 cars. So remember, with continuous variables, the probability of being in a range is going to be that area under the curve. But since we're looking at continuous variables, you're not going to get the probability of an exact event occurring, because the area under a curve for an exact point is going to be 0.